Olá, pessoal. Boa noite. Eu me chamo Amanda Cortcamp. Eu faço parte da diretoria aqui de Relações Internacionais da SP Brasil, como vice-deputy, e também faço parte da diretoria de comunicação também da SP Brasil. E estou aqui para apresentar um pouquinho do Tech Tuesday para vocês. A gente tem aqui como primeiro evento da SP Webinar Series sobre Transatlantic Plugin and Abandonment Operations. Vai ser transmitido através do site da SP Energy Stream, no dia 23 ao dia 25 de abril. Então, quem quiser participar é só entrar no site SP Energy Stream. E tem um cadastro lá também, importante fazer. A gente também tem o nosso evento da SP-ATC, da SP Internacional, comemora 100 anos, inclusive. Esse ano vai ser do dia 23 ao dia 25 de setembro. E já está fazendo as inscrições também para o pessoal lançar o artigo lá. Então, quem quiser se inscrever e apresentar o artigo, só ir lá no site para poder realizar a inscrição. A gente também vai ter o LACSS, né, Latin American Caribbean Student Symposium 2024. Vai ser dia 18 e dia 19 de maio, aqui no Rio, né? Tem mais informações no site mesmo, então vocês podem consultar lá até para as inscrições. Vai ter feira de carreiras, vai ter apresentação do Paper Contest, vai ter também o Petro Brawl lá, regional, então dá uma checada lá e faça as inscrições também. A gente vai ter também o Petro Games, do dia 6 de abril, no sábado. As inscrições já estão abertas também, é só logar no site da SP Brasil que vocês vão achar o link para fazer as inscrições. Teremos o Petro Brawl e Paper Contest, que foi o que eu acabei de falar anteriormente, dia 19 de maio. A gente tem o workshop de Campos Maduros Offshore, dia 25 de maio e dia 29 de maio. Vai ter o DECOM também, que é o Decommissioning Symposium, dia 25 de junho e 26 de junho. Vai ter o workshop de segurança operacional de postos, 20 de agosto e 21 de agosto. FPSO Simpósio, dia 26 de setembro e 27 de setembro também. Segurança Operacional Offshore, dia 16 de outubro e 17 de outubro. Floor Assurance Technology Congress, 2024. 4 de novembro e 6 de novembro que vai acontecer. Subsea Simpósio também, 26 de novembro e 27 de novembro. E em dezembro a gente tem o SP Awards 2024, que ainda não temos data fechada, mas, né, vocês vão saber pelas nossas redes sociais, Instagram e LinkedIn, quando vai acontecer o evento. E pelo menos os eventos iniciais já estão com inscrições abertas, então é só checar pelo site da SP Brasil, caso queiram participar. E participem porque é bem interessante para aumentar o networking de vocês. E é basicamente isso sobre os eventos da SP. E hoje a gente tem o nosso Tech Tuesday com o Marcelo Jaculi, Marcelo Matos e o Pierre Edwards, sobre Development of Bismuth-Based Solutions for Well Plugging and Abandonment. E vou aí chamar o Pierre para fazer a introdução do nosso Tech Tuesday agora oficialmente e em inglês, porque o nosso Tech Tuesday é em inglês. Então, lá.
Thank you, Amanda. Thanks for the introduction. Thanks for the news. Share with the audience. So good morning, good day, wherever you are. And I hope we'll have a number of people either on today or after the fact for this interesting and timely Tech Tuesday on better material. So I will now introduce Marcelo Matos, and just before I do that, let me tell you a little bit about our next two events with the Tech Tuesday. So the next one in April will be on subsea well run, particularly suitable and relevant to Brazil and the Caribbean and Latin America. There'll be so that should be interesting to everyone in that zone. And then the one after that, which we hope to deliver some point in May, will be about the technical sections at SPE and all you can find in them, students, young professionals, etc. We hope to bring you more information about the technical sections then. So co-moderating today on our special event and session is Marcelo Matos with Petrobras. Marcelo holds a degree in mechanical engineering and is currently finishing an MSc in decommissioning. He joined Petrobras in 2008, equipment engineer, took a specialization course in petroleum engineering in 2011, and worked as a companyman supervising drilling, completion, workover, and well abandonment operations on board floating and jackup rigs offshore Brazil until 2016. After working as P&A design engineer, he's currently P&A advisor for offshore wells at Petrobras and was responsible for coordinating the recent November 2022 revision of the IBP well abandonment guidelines. So, Marcelo, welcome to our event. And now on to Marcelo Jaculi, will be the speaker for today. Marcelo holds a bachelor degree in mechanical engineering and master's and doctorate degrees in petroleum engineering, all from the University of Campinas in Brazil, including a doctoral exchange with the Norwegian University of Science and Technology, NTNU, in Norway. He currently holds postdoctoral fellowship at NTNU. His research has included well engineering, with focus on well integrity and P&A, and also in mechanical and oceanary engineering applications within petroleum engineering, vibration of tubulars, equipment reliability, vessel dynamics. Key points from Marcelo's presentation today will include a panorama of P&A and alternative barrier materials, ABM, which I'll discuss in the event which Amanda mentioned earlier in April. Characteristics of bismuth alloys, qualification as a barrier element, and then finally application and challenges. The talk is probably going to last about 20 to 30 minutes, and then we'll have a Q&A session. Marcelo, welcome. The floor is yours.
Okay, thank you so much for the introduction. I think we are good to start. Yeah, okay. So I would like to thank SP Brazil for this invitation. It was with great pleasure that I received this invitation for this presentation today. I'm based in Norway, as Pierre told us. So it's already quite late here in Norway, but it's still a pleasure to be able to share this knowledge with Brazil. So today I'll be talking about bismuth technologies for well P&A. So the idea is to give some panorama over the technology, what has been achieved so far, and what are still the challenges that we need to address. So I will go through a bit of this, especially concerning the requirements to qualify this material as a potential application within P&A. So, yeah. So, yeah, Gary made an introduction about myself as well, but I wanted to emphasize that I took the PhD in Brazil, and then I had this opportunity to come to Norway, but I had been here before. So it's good to still be able to partner with Brazil and then maintain some level of activity in Brazil. So we have these partnerships between some Brazilian universities and NTNU. So we have some visiting students from Unicamp as well. And it has been very good to continue developing these close ties between Brazil and Norway. We have this early November conference that happens in Rio, and we have some sections dedicated to petroleum engineering as well. So, and then it's good to be part of this ecosystem and helping bridge the gap between Brazil and Norway. I think we have a lot in common in terms of the challenges that we have forward. So it's again with great pleasure that I'm here tonight. And my experience has been in well integrity and numerical simulations. So since I hold this background in mechanical engineering, from the very beginning when I was taking master degree, PhD, I always had the interest into working with applications of solid mechanics, fluid mechanics within petroleum engineering, and then to develop this numerical background. And then here I have the opportunity to study how these well barrier elements perform, especially for these newer technologies. And then I would like to talk a bit about SWIPA as well, which is the project that I'm a part of. It's the Center for Subsurface Well Integrity Plugging and Abandonment. It's a center for research-based innovation. It's a type of project that the Research Council of Norway funds here in Norway. So they open a call for this kind of centers, and then a lot of institutions and companies join together and make a proposal for the Research Council, what they want to achieve within the center. And then, as you can see on the bottom, we have like several institutions here from Norway that are taking part into this center, and we have a lot of other industry partners that you can find on our website. And the focus of this particular research center is regarding the performance of well barriers. So we have some work packages that are listed here. I'm part of the first one where we studied potential new materials. So there is other people also studying other potential materials. And then it's basically our goal to test these new technologies, see how far they can go and what kinds of advantages and the shortcomings they have compared to what we have already available in the industry. So then we have some people working with Bismuth, and by coincidence, we just had our annual report released today, because this week is also our annual conference. So then they release the annual report from the last year, every time they have this conference in March. And it's a big coincidence that they released this today and we are on the cover with Bismuth. So I think it was funny to include this in the presentation tonight. And most of the content that will be on this presentation is available on this particular journal article that we just published. It has been made available in January. And it was one of the reasons I think that I was approached about this presentation here. So if you want more details beyond what I'm going to tell during the presentation here, I invite you to go there, download the article. It's open access, so you can find more information there. I will be more brief here during the presentation, but there is more content there. So to start as an introduction here, I would like to talk about a bit about the scenario here in Norway. So here there is a big concern right now regarding P&A, because we have a lot of wells that need abandonment in the short future. And then due to this increasing demand, there was the idea of starting this research center, which could research new technologies to fulfill this demand of new P&A activities. So this became something that is very big in Norway. And as I understand, it's also something that is very big in Brazil, and I believe especially onshore. And then I believe Marcelo will be able to comment a bit more about this after the presentation. But I understand that it's also a big demand in Brazil for P&A. So again, I think it's a good topic that both Brazil and Norway are very interested on and can cooperate. The problem so far, and that has been posed to us, is that since we only have cement as the prime material for P&A, and then you have all these other initiatives for alternative materials, we actually need to test them, because there are some concerns of if cement will be able to hold its long-term sealability. So there is a lot of research being done about cement itself, how to improve the integrity of the well that was abandoned with cement, and how to improve the cementing job quality as well. But at the same time, we should also be looking for other potential materials that could work as a replacement for cement or even in combination with cement. So that's where Bismuth comes from. And then the major problem here is that Norsok G010, which is kind of the baseline for us here in Norway, and I believe that is much followed in Brazil as well. They claim that for alternative barrier materials, you have this table 55 that you can find on the latest revision, with very steep qualification requirements for any alternative barrier material that is not cement. So, and then of course you need to use the cement as the benchmark. So you need to prove that your technology is as good as or better than cement. So if you want to use it. And then there has been a lot of studies for many different types of plugging materials. So bismuth is within a wider scope of metal plugs. So you have bismuth-based alloys, but you also have other types of alloys. And then there are, of course, other materials in terms of resins, gel polymers, thermite, that can provide these well barrier elements that are necessary for you to abandon the well. So the concerns regarding cement can be summarized through this figure here. This figure has become really popular in this kind of well P&A articles because everyone refers to this basically. Because it's very good in terms of pointing out what are the leak paths for us. So if you consider a well that was abandoned with a cement plug, then we have several potential leak paths across either the plug, between gaps, between plug and pipe, or between pipe and the cement behind it, or between it and the formation. But in terms of specifically talking about the plug, our main concern is on these two potential leak paths here. So you can have a leakage through the microannuli. So you have some gap between the plug and the pipe, and then you could have leakage through this gap, since there are two surfaces that are touching but are not necessarily closing this gap completely. Or you could have migration through the plug, and then that's a problem for when you are using porous materials like cement, for example. And then the idea of using a metal plug, and in particular bismuth, is because of two characteristics mostly. So the problem with the microannuli is that if you are able to close it, then it becomes a smaller issue. And then bismuth has a very unique characteristic, that is the capability of expanding upon solidification. So after the alloy is melted downhole, and then you let it solidify, it starts expanding after solidification. And then due to the expansion, you create a better seal with the pipe inner wall. At least that's the idea. So you will be dealing with the microannuli. And then by being a metal plug, you are also having the benefit of a metal being virtually impermeable. So you are not expecting any leakage through the plug. You are expecting your leakage through the microannuli, which may or may not be closed depending on how much expansion you get. So the motivation to start doing this research was to qualify the usage of bismuth as a well barrier material for P&A. And of course, there are other potential applications. You might want to use the bismuth as some form of helping the cement behind the casing as well. So it could be complementary to the cement, or it could even be a replacement to cement. And of course, that depends upon its qualification. And the goal here for us is to study the sealing performance of these bismuth alloy plugs using laboratory tests in combination with numerical simulations. So we have been going through these two approaches, and I will explain why later. But that's basically the goal of our research group that is focused within bismuth inside this center suite. But one big challenge that we had from the very beginning is that there is very little literature about bismuth in this application. So, well, actually, there was no literature about bismuth on this particular application. But you can find a lot of information about these bismuth alloys if you look at other applications, because these bismuth alloys have been used for a few decades on soldering, because they have low melting points, so they are very good for soldering. But aside from that, you cannot find anything like what we are trying to do here. You don't have a plug made of bismuth to plug an oil well. This has not been done before. So then we are starting from very little literature and trying to build up on top of that by performing lab tests and numerical simulations. And then our idea as a research center, since we are very academic oriented, our idea is to collect these findings, and then perhaps lay some groundwork that others can build upon to serve as some reference for the industry, and of course, march towards the technology eventual qualification in the long term. So if you never heard about Bismuth, don't worry. I had never heard about Bismuth before joining this project. So Bismuth is a material that is very unique in terms of characteristics. So the bismuth is a brittle material that melts at a very high temperature. Not very high, of course, compared to other metals, but to a temperature that it would be unfeasible and unsuitable for downhole environments. But then bismuth can be combined into low melting point alloys. So you have, for example, the bismuth tin alloy, which is the one that we have been studying the most. But you have other types of bismuth alloys. But these alloys have this very unique characteristic of expanding up upon solidification. And this is something that doesn't happen with all metals. You have very few selected metals in the periodic table that display this kind of behavior when transitioning from a liquid to a solid state. I think it's bismuth, gallium, antimony, and I think a fourth element. I don't remember which one. So this very unique characteristic gives this kind of low melting point alloys very unique properties. So then our focus has been on the eutectic bismuth tin alloy, and then there is a reason for that, because eutectic alloys are better in terms of control over the melting and setting the plug process, because an eutectic alloy melts at a single temperature. You have this. As long as there is any solid material while you are melting it, it won't change its temperature. So you won't have a mix of solid and liquid phase. That's what it means being eutectic. So we start using this as a starting point because it's what some service companies were trying to investigate. But we know that by now the companies are also moving towards other types of bismuth-based alloys. But we have focus on characterizing this one because I believe that whatever procedure, whatever results we get from this one can easily be extended to other types of alloys. You just need to follow the same lab tests, run the same simulation. So we basically have a recipe to test any alloy that you would like. Then why bismuth? Because of this main feature of expanding upon solidification, like what happens when water becomes ice. And the idea is that this can improve sealability. So if you remember from the picture, the idea is that by having this alloy expand, you are reducing the gap between the plug and the pipe inner wall. And since it's impermeable, basically since it's a metal plug, you don't get any leakage through the plug, and then probably you can reduce the plug length. So I'm saying probably because it's something that we are still studying and it's still being tested in the field. But if you manage to reduce the plug length, then that's a very good thing because you are, of course, saving material, and then it makes the solution more competitive compared to cement. So if you have a plug of cement and a plug of bismuth of the same size, the same mass of material, then of course bismuth is going to cost more than cement. But if you're able to shorten the plug and also perhaps shorten the operational time to settle this plug, then you are saving money. And then this becomes a very competitive solution. And then we have an example from Aker BP that deployed some 2 meters plug in Norway. And it's on this reference that I can, if anyone is interested, can contact me. And they showed some promising results. But it was an initial test. The plug that they built was an environmental barrier, so it was at the very top of the well, not like very deep downhole as the last plug that you have there. But in any case, and they also had to keep the cement plug as well, because you still cannot deploy only a bismuth-based solution. You have to deploy the cement and the bismuth-based solution. But they were able to verify some good results on this. They haven't seen any leakage towards this plug, and they were also able to fix some problems of sustained casing pressure that they were observing on this particular well candidates that they selected to deploy this bismuth plugs. And it also, this whole discussion of plug length is due to the NORSOC proposing how a cement plug should be. So you have some requirements in terms of plug length. And then at another point of the NORSOC, it says that any alternative barrier material should have a plug length that is comparable with cement. But of course, we're not going to settle a bismuth plug of 100 meters here. We don't want to replace a cement plug for such a large bismuth plug. We want this to be shorter. But then, of course, we need to do the proper investigation for this to be achieved. To settle the plug, the literature, not just the literature, but like patents that were made for this technology, they basically propose two different methods. One would be pouring the melted alloy already inside a container and then lowering this into the well. Or you have the option to melting the alloy inside the well. So you lower it in the solid phase, and then you melt it downhole using some electric heater or some thermite reaction. So I have a video here from one of the service companies. You can visit them on their website, but I do not represent them. I just think that the video is very good at showing this. So I'll jump straight to the point here. Where they show where the technology is being placed. So you see here that a tool is lowered into the well. And then when it reaches the position where you want to set the plug, you are going to see here that, so you see this silver-like material here is the bismuth alloy. It's you lower it kind of like a pipe, which is encasing which has some hollow portion inside, and then you have the rest of the tool here, and then you start a thermite reaction from inside, and then this melts the material that is in this pipe kind of stuff. So you see now it becomes liquid, and then it's gonna fill completely the space inside the casing. So that's the idea. You are gonna create this plug here, and then you are gonna close the whole gap here. So you can see from the tool here that you had some gap here in black, but then the idea is that this closes the gap completely after solidification. And then that's it. You basically created the plug. And as I mentioned in the beginning, we have applications for setting a plug. It's possible to apply this to settle a plug inside the casing, but you could also use this in place of the cement behind the casing, because it could even help a poor cementing job by pumping extra bismuth, or you could even pump bismuth within the cracks here of cement, which is something that was also investigated by them. But one important aspect here that it kind of differentiates from other sealing technologies and for other alternative barrier materials as well, is that there is no type of chemical bonding between bismuth and steel. They are two metals, so they are not going to interact with each other. You are basically setting a plug there by allowing this solidification to happen, and then it will be a combination of the bismuth expanding inside the pipe towards the pipe inner wall, and then friction, of course, because it's going to happen. Friction is going to happen between the two metallic surfaces. And this is going to provide us what we call the hydraulic shear bond strength. In other words, it's what's going to hold the plug in place. So there is no chemical bonding, but there is this kind of adherence between the two metallic surfaces. So, of course, you might think, oh, is pipe roughness something important? Yes, and it's something that we are investigating. But we do believe that depending on how you leave the casing inner wall, that roughness will be a key factor on how much pressure this plug can withstand later. And then, of course, you also need to be worried about contaminants. So if you have to clean the casing before settling the plug, then you have to take these two things into consideration. Like, you might not want your casing inner wall to be as polished as possible, because that might not be able to settle a good plug. But at the same time, you want to try to avoid contaminants so it doesn't undermine the plug strength. So yeah, there is still some discussion on what's the best downhole conditions before you set the plug. So here, just for curiosity, we have some pictures from the lab. So that's the test that we have been running. You have some pipes, some pipe samples that were provided to us. And here you have the alloy that we buy from a manufacturer, which is the authentic bismuth tin alloy. And you can see here the 137 is the melting point. And then we melt this, pour into the pipe, let it solidify, and you create a plug like this. So that's basically the idea. And then we take this pipe with the plug inside, and we go to the machine to perform the hydraulic push-out tests. So basically, you're applying pressure at the top of the plug, and then you see how much pressure it can withstand. Or you also measure the leakage rate through the pipe, so you can collect fluid at the bottom and see how much is leaking. And then we take this to the software, and we try to match the laboratory tests with the numerical model. So at least if you are able to match the results in laboratory conditions, then we know that we kind of have a good material model for bismuth. And then we can hopefully use this simulation knowledge to simulate also other conditions that cannot be easily tested on the lab. Yeah, and from our observations, and I think that's basically the main goal of our numerical model is what we can provide in terms of characterization of this alloy. And based on our experimental and numerical observations, we realized that this particular problem is very unique in terms of the characteristics of this alloy. And then it can be characterized by these three combined phenomena. So the first one is the expansion upon solidification that I talked so far. So it's a very unique quality of this alloy, and it's its main selling point, basically. But one thing that is very important that manufacturers claim is that this expansion, it doesn't happen instantaneously when the phase changes. So after the liquid alloy becomes solid, it's not going to expand completely, but it's going to expand over time. So you are expected to have some improvement over time. However, you also have creep behavior, which can be relevant for this alloy depending on the temperature that you want to apply this for. So if you have temperatures that are closer to the melting point, so remember the melting point of this particular eutectic bismuth tin alloy is 137, 138. So if you are operating at a temperature above, for example, 100, you're going to get a lot of creep behavior. And creep is something that undermines the capability of the plug of sustaining the loads. So then you're going to see a decrease in the amount of pressure that you can apply on the plug before you actually break the seal. So this is an effect that is competing with the expansion, and it kind of depends on the temperature condition where you are setting the plug. And finally, on top of all that, we have an effect of aging, because any metal material is may lose its properties due to the high load over some sustained long period of time, and also if you are applying this at high temperatures. So then it's gonna lose its properties, and therefore it's gonna decrease its sealability capability. So its sealing capability. So it's something that it also needs to be investigated. There are some data, you can find some data on this, but not completely. So, but it's an important effect that you have to take into consideration, especially since this plug is going to be there for a very long time. So you need to take into account the degradation of this particular material. So in this literature review, we put some very preliminary results that we achieved here by performing some leakage tests with nitrogen gas, and we had plugs of similar length of bismuth and cement, and we saw that the leakage rate through the bismuth was much lower than it was for the cement. But of course, I have to make a big emphasis here that this is applicable for that specific test condition. So, and then you can find more details on this particular publication that I mentioned at the beginning. But this is going to hold true for that particular condition. And then it's up to us here to study how do we scale this in terms of reducing the plug length. So for example, if here we are comparing two plugs which have similar plug lengths, that's good. Okay, Bismuth is going to behave better, but it's not necessarily the best solution, because we actually want to reduce the Bismuth plug length. And then when we reduce the plug length, then it might be more comparable with cement. So then it's something that you need to investigate further. But the results that we saw from the very beginning, and both from the lab and also from the field applications that were done by AccurDP, shows that Bismuth has a lot of potential in terms of reducing leakage rates. So yeah, that's the whole motivation behind pursuing this technology. So I would like to continue by telling at what point this technology is currently. So if we think about a qualification process according to the NORSOC framework, there are some criteria that alternative barrier material must follow. And then some of this criteria is already kind of answered by what has been done so far. But some others still need further investigation. So it's this panorama about the technology that I would like to bring here. So if we talk about that an alternative barrier material must exhibit long-term integrity, well, that's the big question that we're still trying to answer. But I think that's like the final answer that we have when we collect all the data about this technology. So will the Bismuth plug be capable of holding long-term integrity? We still don't know, but there is a lot of potential. So that's why we keep pursuing this technology. Our alternative barrier material must have a very, very low permeability. So that's a good thing. From the very beginning, you can say that the material satisfies this condition because a metal is virtually impermeable. So you are good on this one. An alternative material cannot have too much radial shrinkage. There is some accepted limit on this. So you have shrinkage from cement. It's a well-known effect. Then there is a lot of studies on how to improve the cement. So there are a lot of additives that you can put on cement to combat this particular shrinkage. But for the case of bismuth alloys, that's also solved from the very beginning because the alloy expands instead. So you have no problems with radial shrinkage. Then sustaining mechanical loads, that's up to the conditions of where you're going to apply. But in general, based on the lab tests that we did and based on this field application from AccurDP, we can say that, yes, the plug is able to sustain the mechanical loads that are expected from it, in the same way that cement can also withstand these mechanical loads. So this one, we have collected a good amount of data to at least give some check mark on this. Like sustaining the mechanical load is not the issue. Chemical stability, yeah, then that's still something up to debate because, for example, if you were talking about pure bismuth, then you don't expect corrosion from pure bismuth. It's resistant towards corrosion. But then after you start adding other elements into the alloy, then it might not be resistant to corrosion anymore. So I think this deserves more investigation, especially for the bismuth tin alloy, but also for other alloys that the service companies are probably investigating as well. And this is important because you don't want your plug to be consumed by corrosion. So it's something that is still up to debate. Bonding to tubulars. So any alternative material must be able to bond to tubulars. But as I explained in the beginning, there is no chemical bond between bismuth and the steel. So because there are two metals, they are not interacting with each other. We're not welding them together. So the only type of bonding that we have is in terms of a mechanical bonding. So it's an adherence between the plug and the pipe inner wall. So we have friction holding them together, and we can say that the plug is bonding to the tubular due to friction. And finally, the effect on the tubular integrity. So any alternative barrier material must not damage the tubular in which it's placed. So this is something that still needs more investigations because we don't know yet the full effects of having this plug expanding inside the casing. It could damage the casing, it could damage the cement behind the casing, or for example, it could close cracks in the cement behind the casing. It could close microannuli between the casing and the cement behind it. So there is both the potential of doing damage and both the potential of solving other issues. So that's why I also believe this needs further investigation. And then we also list some other further challenges that would still need to be tackled. So one of the things is that we don't have enough data on different bismuth alloys. So at the beginning I said, okay, we don't have any data at all. So now we have some data on one type of bismuth alloy. So then there is still a long way to go if you want to qualify bismuth alloys as a whole, because there are different types of alloys with different melting points. So they potentially have different applications depending on particular well conditions. There are some issues related to the melting process. So you saw from the video that you are lowering a tool, with the bismuth alloy, and then you are melting it, and then it falls into the well, and then it closes this annular gap. But there is the potential for this heater to be stuck there. You want to retrieve this before the alloy solidifies, but if it solidifies first, then you are probably going to have the heater stuck there. So that could be an issue. You could have a problem with the thermite if you are using, for example, a thermite technology to melt the alloy downhole. You could maybe not be able to melt everything depending on how you ignite the thermite. You also may have problems with heat propagation. So if you're using, for example, thermite, you're generating a lot of heat. This is going to be dissipated into other well barrier elements. So this could be an issue for the casing itself, for the cement that is also behind it, even for the formation perhaps. So it's also needs further investigation. You might have some problems with thermal shock if the alloy cools down too fast. So this is something that we observed in the lab, and it could be an issue as well when placing the plug downhole. So another heat-related problem. We could have some problems when setting the plug. If you have some leakage around it while the alloy is still solidifying, you could have some shift in the barrier position. The alloy the plug might move from the intended position, and then you don't place the barrier where you want. It's kind of similar to what also happens with cement. Sometimes in some cement jobs, you are unable to put the cement in the position that you wanted and to reach the top of cement that was expected. So the same could happen here when setting this plug. And then you have the effect of the expansion on tubulars and the cement behind the casing, which I already addressed in the previous slide, but it's a concern here that needs more investigations. And then you have some problems related to the material properties. So you have creep behavior, which is relevant for high temperatures. So you might be unable to use a particular alloy in a well whose temperature is closer to the melting point, because that could damage the sealability of the plug. And then there is some threshold temperature that you can use this plug safely. Otherwise, you need a different type of alloy for that particular application. There is a concern about liquid metal embrittlement. So this is a phenomenon that happens when you have a solid metal, so in the form of the casing steel, and then you have a liquid metal in the form of the molten alloy. So there are some known interactions in the literature where some liquid metals can damage solid metals and damage their properties. But the interaction between liquid bismuth and solid steel is completely unknown. No one has investigated, at least it's not published, anything regarding if liquid bismuth can damage solid steel. So I think this is also a challenge that needs addressing. And then again, the problem of corrosion reducing the plug length, it's something that you don't want to happen, because then if your plug length is reducing, you are losing the intended sealing capability that you designed at first. And finally, there is also, then if you think about costs, which is of course usually the highest barrier for any new technology, we're always thinking about cost. So if everyone starts using Bismuth everywhere to plug our wells, then we might have some issues regarding the availability of Bismuth and its cost. So we need to make sure that the technology is competitive compared to cement materials. So at least this technology can, even if it's qualified in terms of the technological aspect, it might not be feasible from a cost point of view. Then you use this under specific conditions. If you have a very problematic well that you need to do the P&A, or I don't know, some particular condition where you are okay spending more because you need the further integrity. So of course, cost is an issue that has to be addressed. So to conclude, I would like to say that, well, the idea here was to present some preliminary results, our preliminary feelings about the technology, so we understand what's happening behind this metal-to-metal seal between the casing steel and the bismuth plug. But as I explained, there are several unique mechanisms that are not seen in other applications, and some of these are very unique properties of bismuth alloys. So there is a lot of things to investigate for this particular application that are you cannot extrapolate from other sources. And then some things that are interesting that we intend to investigate here is the effect of pipe roughness, if this improves the sealability. And when I say pipe roughness, I mean the inner wall of the casing. And also the effect on the cement behind the casing. So that's something that also needs to be verified. And from a numerical simulation side, from a numerical point of view, I do understand that the companies also run their own simulations. So we believe that if we can provide some groundwork on how you model bismuth, if you want to run simulations for this particular problem, I think that's a very good contribution for the industry, because you won't be able to test all the conditions, you won't be able to test all the alloys. But if you have the data and you have the procedures, if you have a recipe on how to do this, then you can run all these scenarios using whatever software is available. So again, I would like to thank very much the SP Brazil section for this invitation. It has been a pleasure. And I'm not sure how many comments we have there, but then I'm open to questions now. Thank you. I do believe I went over the time I was expecting.
Not really.
Yeah,
it was great. It was great, Marcelo. And in fact, we have a few questions. Pierre, do you want to make a few comments before entering the questions?
You are muted. You are muted.
Sorry about that. Yeah, so absolutely, great presentation. Thank you, Marcelo, and I think it will captivate the audience, and we're not gonna bear you grudge for going over time with such good content. So you mentioned the collaboration between different regions having the same problems, etc. And I think your own career path at this point has been a good illustration of that, and need more similar collaboration initiatives between various regions of the world, because we all have issues to solve. So there are future careers in that kind of jobs, by the way, research and tackling integrity issues, tackling P&A issues in the future. So anybody listening from Latin America or anywhere, or Brazil, students, etc., this will be an area where we need bright engineers to help. And then just before we go into a Q&A, the topic of alternative barrier materials and how to test them and how to qualify them, etc., will be a specific topic of an hour and a half of discussion at the PNTS virtual workshop in April. Marcelo, do you want to take on to the first questions, or?
Sure. Yeah. So with that said, it's no surprise to see that the first question that we received is from Matt in New Zealand. So just expressing how the subject is relevant and interesting. So he's asking, is the reason for having to place a cement plug in addition to bismuth due to cement being a current proven accepted barrier as a backup to the bismuth in these testing phases? Is the goal to eventually just require a bismuth plug once that is proven? So basically, he's trying to understand how bismuth and cement they are going to interact. Are we intending to replace bismuth and cement by bismuth, or is the intention to have them working together, and then how would we combine them? So if you could please elaborate on that, Marcelo.
Okay, yeah. So I think his question splits into two phases: a testing phase and let's say a deployment phase once the technology is set. So from the test phase, I think it was the first question. Then during testing, if you want to test the bismuth plug nowadays, you have to do this with cement, because according to the current standards, we cannot just deploy bismuth as the sealing material without having anything that is approved as a sealing material, since bismuth is not approved. So at least from the Aker BP field test that they did, they still had the cement plugs in place, and then they added the bismuth plugs on top, and then they could monitor what was happening along the bismuth plug itself. So then they could see if there was happening a leakage only on the bismuth plug. So that was their way of testing this on the field, but at the same time still complying to the standard way of doing the P&A. But when the technology becomes proven, then I guess it's a big debate, because if you ask someone that is passionate about this technology, they will say that their goal is to have a technology that is as good as cement and perhaps replace cement. But then, of course, there will be some convincing from the other side in terms of what the operators want to do. And well, cement is proven, cement works. We know that there are shortcomings, but it has been the standard, the prime material in the industry so far. So I don't really foresee a future where they're going to simply replace cement for another material. But instead, you might have these very specialized cases where you need you have some poor cementing job, and then you want to put the bismuth plug in place to improve integrity. And then you have these cases where you could use other alternative barrier materials as a way of creating further redundancy in terms of your barrier elements. But I don't see bismuth easily replacing cement, because I know there will be a lot of resistance from the industry itself of just replacing a material that has been used for decades. But maybe you could give a perspective from Petrobras.
Well, I think it's a great question from Matt, and I want to stress two points. The first is, if we had to qualify cement, cement has been used for a long time, but if we had to qualify cement as a new product, we might find it difficult, in some cases, because it might not be perfect for every job, and gradual innovation versus leapfrog innovation. At this stage, I think reasonably in gradual innovation and how to provide new solutions, find new solutions to problems we have, and bismuth seems to be offering. It can be used as a base, it can be used as a combination for constituting barriers. So there was another question by Tiago in Brazil, who was asking, how would, in your opinion, bismuth compare with magnesium oxide, special cement slurries, which provide some degree of expansion and provide better isolation than conventional slurries?
Yeah. So this is I have to give a very unfortunate answer to this one, but no, we were not able to compare with this very particular types of cement, simply because we were unable to get the materials in the lab. So, but it's something that we would like to test. Yes, if some company is willing to provide us with the right materials, we are open to that. But of some of our tests we had to do with the materials that were easily available. So we just used some ordinary Class G cement, and that's it. But of course, if you start including all these proprietary types of cement that have much better conditions, way better behavior than the Class G Portland cement, then of course then cement becomes more competitive with bismuth, and I think that's good, because then that's where the technology can really shine or not, and then that's when we see if it's going to be competitive against cement. So then I think it kind of falls back on the previous question, if you are replacing cement or not. So perhaps no, perhaps this expanded cement is enough for most applications, and then we use the bismuth as a very specialized tool for very specific applications.
But for that specifically, on the question, the debate, how high, how long does my barrier element need to be for a specific application? Then if we were to test cement, then we would need to test a specific formulation, and then it's an issue for labs like your own to get their hands on proprietary additives, proprietary formulations, because cement service companies do not want to give out their additives that easily. So you'd have to sign.
Exactly.
They have to come. The additives would need to be delivered by a military escort, and you need to sign multiple NDAs. It's complicated.
Yeah.
If I may add to that, and Pierre, I guess it also relates to your previous comment on maybe aren't we being too much condescendent in terms of the qualification of cement? Cement has been used for long, and everyone seems to be happy with it. But when we start adding or changing its properties, putting more additives, are we still preserving its original properties or not? So are we qualifying these other materials that we are adding to cement, so to be sure that it's fulfilling the expected requirements for permanent plug and abandonment? I'm a little bit concerned on that. I see when we are stressing a new material, and in this case today, Marcelo just presented what's being done with bismuth. I see that we are looking about everything. Seems that we're putting a magnifying glass and looking all the spots, trying to cover everything. And I'm really not sure if we did that for cement. So maybe I'm being rhetoric. The answer is no, we didn't do that for cement, but everyone seems to be happy with it. So it's a nice discussion, this qualification of alternative barrier material.
Everyone, I think it has simply been accepted as the default material. It doesn't mean it's the only one, and it doesn't mean the way we've deployed it in the past has been always very good. And if we look at well into the issues in the world, they're so common that one can think, maybe cement is not, if deployed without care, it might not always behave in the way we expect. So a question from Federico in Brazil, Marcelo, he's asking about how can thermite be used to melt bismuth, considering it's producing such a high temperature plasma?
Okay, yes. So this one also falls into some proprietary knowledge from the company. So in the video that I showed, that particular company uses thermite, but they explained that they also have some additives on that thermite. So its ignition point is way lower than this. I don't remember the exact temperature, but it's something that is much more achievable downhole. But then there are also other companies that are studying using an electric heater. precisely because they are concerned about the heat dissipation that is generated from the thermite reaction. So then you basically have this two ignition process. They are kind of competing against each other, and they have their own advantages and shortcomings. It's much easier to melt using thermite, but then it's also has some other disadvantages that need to be taken care of that the electric heater doesn't have. So then, again, since it's a very new field, you have all the service companies trying to be the leading company on this technology. Then you have all these competing ways of settling the plug, and I'm really curious to see what's gonna be chosen as the best way of setting this plug.
Good.
Marcelo, so Matos, because there was a question or something, a comment that the other Marcelo made earlier about your P&A experience in Brazil. And I know for a fact that at least one provider has established business in Brazil with probably ambitions to be, more present in the domestic market. So have you used Bismuth in Brazil? Do you see an application for onshore P&A activities?
Yeah, in fact, from Petrobras side, yes, we started applying bismuth in one of our wells. There was a recent publication from the company who executed the services, so it was a very challenging scenario, and they were successful in setting the bismuth plug. And of course, when we are working in P&A, it's everything that we want to have is the more technology that we have available, the best for us. So having bismuth available as an option, yeah, it's great. There are a lot of benefits in comparison to conventional plugs, but on the other hand, there are maybe these uncertainties that Marcelo greatly presented today. So for the long-term perspective, maybe we are not 100% confident, and that's the reason why the industry is putting so much effort and money trying to understand that. So basically, yes, we are starting to apply it in Brazil. For onshore, maybe there's an opportunity there, but then of course cost is something that we need to take into account. So basically, when we are talking about onshore, we are talking about assets that they are very much sensitive to cost, and then bismuth plugs, they are not cheap at all. So maybe this is going to be a limitation for bismuth. Apart from the obvious sizes, the schematics that we have in our subsea wells, they have bigger diameters in comparison to our onshore wells, and these maybe reduce the applicability, the current applicability of the bismuth plug in the onshore environment. But anyway, it's something that I definitely see getting traction, and I expect the same here in Brazil. There are, as I've mentioned, there are other technologies competing with bismuth, but we should see it being applied more and more. For permanent abandonment, we are studying that, and we are not alone in this. We see this as Marcelo presented. We see Aker BP, for instance, in Norway, maybe leading this process. And there are some advantages, but definitely we need to understand, we need to be confident for a long term, specifically if we want to get rid of cement. So replacing cement by bismuth, we need to be very much confident on it. Yeah, so I guess this is what I can comment from Petrobras perspective. I don't know, P, if from Trident perspective you have any experience with bismuth plugs.
No, so I would say, yeah, again, I'd go back to, gradual innovation versus leapfrog innovation. I think it's a great tool in the toolbox, and we can start using it for this, but there are still areas which definitely need more work. And I'll go back to what you mentioned, Marcelo, about at the lab regarding application. I mean, delta P, what are the boundaries for a specific application that require more work? Aging, also, we don't completely understand what's going to happen. You've mentioned corrosion briefly and touched on CO2, H2S, but also any corrosive additional elements that might be present that are difficult to completely model in the lab unless you know exactly the fluid composition, because chemical interactions can be complex. I was thinking H2 also at some point. And then one point you have not mentioned at all, but which would be a key point for constitution of barriers for P&A, it's the interaction with the formations. So caprock, wherever it was set, then there might be some interaction with formations. You mentioned you focused mostly your work on casing, which is fantastic, but then it's a lot more complex with rock.
Yeah, there has been one particular study about bonding with formation. I think it was a guy from SLB. They published, like, I think 3 journal articles about this. And it's the only work about interaction with formation. But yes, I didn't mention this here, but there is this one particular study about interaction with the formation. So there are some people concerned about this as well.
Definitely, and there'll be, so there's been more work done in the US about that, and one of my former colleagues at Shell, Erigan, will present at our upcoming workshop about this, about the effect of heat on caprock. If you want to find.
Yeah, maybe Marcelo, I don't know if you can maybe discuss a little bit on that, but considering the application where we set the bismuth inside of the casing, so at the same time we would be relying on the cement and on the outside of the casing. And as you presented the length requirements for cement, we have the 50 meters, 60 meters, depending on the jurisdiction where you're operating. It's completely different from the typical lengths of the bismuth plugs that we see being applied, which is around 1 meter, 2 meters. So thinking from a permanent abandonment perspective, where the basic requirement is to reconstitute the caprock, so basically is achieving that cross-sectional barrier. So how do you see this happening when we have an element in the inside, which is 1-2 meters, and on the outside we have an element which is currently required to have not less than 30 meters, let's say?
Yeah, that's a very good one. So, well, so far, since the tests cannot be done using just the bismuth, this, for example, 2 meter plug length is completely arbitrary at this point, because they could test any plug length that they want, since they are actually relying on the cement that is there. So let's say the standard P&A was done. So let's try and see what happens with a 2 meter plug length. But then replacing, if you replace only the inner cement plug by a bismuth plug of a much shorter length, but you are still relying on a cement plug that is much longer, then of course the region where you have this overlap and you create your barrier envelope over, it's going to be a very short region, and then you could potentially get some influx through the cement, through the casing, and then above the bismuth plug. So yes, that's a big concern in terms of how to address this in a well integrity perspective when you are thinking about the well barrier envelope as a whole. So, but I think I have no easy answer for that question, because I think it kind of, but it's very interesting to think of this in a wider perspective, because it's not just about the plug itself. Is the bismuth plug able to sustain the pressure? Is it able to guarantee sealability? Yes, it could be. But how does it work in conjunction with the other barrier elements? And that's a way, that's like a step ahead. But we need to get there eventually, because we don't know how it interacts with the other well barrier elements, and if we will be able to secure the barrier envelopes that we're looking for, especially if you're looking at the way we do in Brazil, the way they do here in Norway. These are considerations that we need to do in terms of envelope as a whole.
Yeah,
Absolutely.
totally agree. I guess it will be, sorry, Pierre. I think it would be the next step, and this question, I think there's totally a link with Matt's last question. He's asking about to achieve the adherence of the bismuth to the pipe. Could you punch or perforate the casing prior to setting the bismuth so that the bismuth flows into the perf tunnel and providing some additional shear resistance? So maybe by doing that, we would not be having bismuth in the inside and cement on the outside, but in the outside you're going to have maybe a hybrid material mix between bismuth or cement, or maybe only bismuth, depending on the depth where you have perforated the case. So it might be a way to address that topic. So how do you see that, Marcelo? Do you believe that this might be an approach capable of addressing these issues? Do you see any other benefits or risks on doing that?
Yeah, I was while you were posing the question, I was searching here for a picture that I think illustrates this exactly. It's exactly his question here, so I think I can share here
Bismuth flowing through cracks.
Yeah, because this is an application that these people from this company BISN they tried to investigate, and I think they did this, and I think I can put it here. So yeah, so you have exactly this. They made this perforation within the inner casing, and then they pour the bismuth there, and then you allow it to melt and fill the annulus behind the casing as well, the annulus B. But you could have cement there as well, so you could use this to remedy the cement behind the casing as well. It could be another application. So regardless if you are replacing cement or even improving cement. So again, it's another tool in the box. Yeah.
I would say exactly, but I would say we would definitely need more work, because there were so many attempted remedials, at poor cement job where you perforate and you try to squeeze cement and it doesn't go through. that it would be hard to be sure that the bismuth actually goes into any of the poor cement, for instance. So yeah, more work would definitely be needed for that. All right. Well, time. I think we've used very well the hour which we had for this discussion, and I trust it was very educative to everyone. So thank you very much to both of you, Marcelo, for being on this call. And conclude now. Quick reminder that our next, as I said, our next two Tech Tuesdays will be, I think, also very good. One will be on sea response, particularly applicable to Brazil. What is a subsea well emergency in a country like Brazil or in the area? And so we'll talk about that with Brett Morey, with Darrell. And then after that, the Tech Tuesday in May will be a presentation on the various technical sections with SPE and all the various disciplines that are covered there, which are a great way to learn, network, ask questions, etc., and a great way to develop for anybody. So thanks again, both of you, and wherever you are, I wish you a good day.
Thank you. Thanks for the opportunity. Bye. Bye.